Well, I'm really excited to be here. My name is Matt Langione. I'm a partner at BCG and Boston Consulting Group. It's a global firm. It is, we have 25,000 employees. We're in 90 offices all around the world. Our first office was in 1962 in Boston, which is where I'm from, it's my hometown. But our second office, it wasn't in New York, it wasn't in Chicago or Los Angeles, it wasn't in London. It was actually right here in Tokyo. And that was 1965, and we've kept really close ties to the business community here ever since. And so it's just with great pleasure that I have the opportunity, and thank you from QCware and Q2B for inviting me to talk to you about a topic that is really, really top of mind for us. That's quantum computing. And it's top of mind for us when we think about deep technologies, vanguard technologies that have the potential to disrupt a broad range of industries, in the next months, years. And so I lead our deep tech practice for North America, and I lead our quantum computing topic globally. Now, whenever I introduce quantum computing, I think it's always important to ask a preliminary question, which is, well, what's wrong with classical computing, traditional computing? From the looks of it, you might answer, well, not much. For the last 50 to 70 years, classical computers have just been getting smaller, better, and faster, driving the economy in a way that really nothing else has. But that period is set to come to an end or to slow down. And that's because, of course, transistors have become so small that they're fast approaching the size of an atom, which is a hard physical limit. Many think that Moore's law is set to kind of peter out by 2025, or at least in the way that we've expected it to. And so, even right now, it's more expensive to uphold Moore's law than in the early days by a factor of 18. And this slowdown comes at a time when industries are more reliant than ever on computational speed-ups to drive discovery, innovation, and value creation. So while in general, since 2012, as you can see on the chart, the S&P 500 is up 200+%, there are a set of industries that, for want of a platform that accelerates discovery, have struggled to keep pace. If you look at pharmaceuticals, for example, it costs 3 times as much to discover a drug today as it did just 20 years ago. That's a rise of 9% over inflation year over year. In finance, there's a higher cost of equity than return on equity for more than half of banks. That rises to 60% in Europe. In materials, the demand for EV batteries is greater than the supply by a factor of 10. And you'll hear a little bit more about fertilizer efficiency. I'm not proposing that quantum computing will be kind of the white knight of innovation in all of these industries by any means. It's just to say that when you hear the excitement about quantum computing in the business community, it really comes from a place of deep need, a need for a platform for innovation. Quantum computing, we think, is one of the best candidates. And here's why. Quantum computing has the potential it is an exponential technology that has the potential to operate exponentially faster than classical alternatives in a number of key places. Let me give you a few sort of kind of eye-popping use cases that I think have really kind of turned me on to the technology and have really gotten our attention as a consulting firm. So let's just take in materials design fertilizer synthesis, which is one of the hallmark problems in the science of climate change. The way that fertilizer is produced today comes at an enormous cost, both to the companies that produce it, $100 to $300 billion a year, and to the environment. 3 to 5% of the world's natural gas is expended every year on fertilizer synthesis. Now, here's the truly remarkable thing. Scientists know in principle how to use computers to discover a more efficient alternative. The problem is that even on the world's fastest supercomputer, simulating all the maze-like interactions of the key catalyst, nitrogenase, would take 800,000 years. On a quantum computer, it could be done in less than 24 hours. So when we say exponential, that's what we mean. It's a similar dynamic in other places, like in drug discovery, for example, where the holy grail is to be able to characterize the entire span of chemical space so that you can find the molecule or protein that could treat any disease. The problem is that in order to simulate that entire and characterize that entire span of chemical space, it would take 5 trillion years. So that's 5 with 4 trillions after it. On a quantum computer, it could be done in 30 minutes. Now, lest you think that all of the problems that quantum computers can solve are these esoteric lab problems, take finance, where risk simulations that banks run can take weeks, sometimes months to converge. There's a famous case of a simulation that started, I think, in February. One of the major banks was telling me about it. They started a major simulation in February of 2020, and by the time it converged, the market was down 30% because COVID had happened. But those could be done in real time with quantum computers, which is just a massive change in the way that we think about risk and think about pricing. And so, while it's true that quantum computers certainly won't do everything, and of course the future is hybrid, it's also the case that there are problems like this in many industries. And we think that even quantum advantage could come as soon as the next year. It may not disrupt industries quite yet, but we think that the time is really nearing and that the future is really bright. And so when we think about that, when we go across, we talk to a lot of potential end users of this technology. And really, I want to emphasize a couple different things. The first is that quantum computers really do one thing much better than classical computers. So the future will always be hybrid, and that thing is calculating large, sparse matrices. It just so happens that large, sparse matrices are really important for 4 computational problem types. And these are things that you'll hear about quite a lot, at least over the next 2 days if you haven't already. And the one is simulation. And this is you use a quantum computer to simulate a quantum system, right? This was one of the first kind of use cases that kind of engendered the dream of quantum computing in the early 80s at some of the foundational IBM, MIT conferences. The second one, and by the way, here, for example, you can think about some of the work that, for example, IBM is doing with JSR on OLED technology, where these light emitters are about 25% efficient now, but with quantum computing, the hope is that could get to 100%. Another one is optimization. These are problems that are well known, things like the traveling salesman problem, where when you introduce a new parameter, every new parameter is a doubling of the search space that a computer would need to be able to sort through in order to come to a solution. Problems here include things like what QCware is doing with Airbus on flight route optimization. It's an important problem because, of course, there are implications for fuel and efficiency. And then the third one is machine learning. And we think that machine learning problems could actually be the thing that makes quantum computing really transversal and applicable across industries, in part because so many important problems have already been scoped for machine learning, that accelerating machine learning has the possibility of really extending the reach of quantum computing. There are also, I think, well-known impacts for cryptography, starting with Shor's algorithm in 1994 that actually has candidly had a big role in bringing about government investment in the technology. Now, I want to just spotlight the finance industry. I think finance industry is one that I think is a good bellwether of the progress in quantum computing. in part because it's not, in a lot of the materials and the chemistry spaces, there are a lot of people that are very conversant in quantum chemistry. But in finance, those are folks that have had to kind of come into these companies more recently. So when you look at, first of all, 8 of the top 10 banks in the world have a quantum computing capability now. And the others are scoping and thinking about it. When you look at graduates from top universities that have quantum programs, the number one thing that they do is they tend to stay in academia. The second thing that they do is they'll go to a quantum computing company like IBM or like QCWare or quantum startup. But the third place is actually that they'll go to banks. And some of them will work on quantum type problems. Others will work on just standard classical problems. But I think that the important thing to note is that a lot of talent is coming into the banking industry because there's a really acute awareness of the potential for disruption of quantum technologies in the space. I also wanted to mention that while it's true, I've talked to a lot of Japanese companies about the potential to play in the supply chain, so supplying quantum devices to the makers of quantum technologies. I think that there's a really, really important thing that everyone should do, which is to say to think really holistically about being a user of quantum computing as well, right? There are a lot of use cases in electronics. I had mentioned the IBM and the JSR use case. There's a number of upstream use cases around materials design, but it's also worth noting that there are downstream use cases as well. More synthetic routes, for example, for manufacturing, pricing arbitrage, a lot of use cases that I think are really worth scoping and identifying. And the reason that I think that that's important to do now, because this is a vanguard technology, and we're a consulting group. Oftentimes when we get brought into an engagement, the time frames are really short. It's like, what kind of impact can you give me this quarter or this month? But with this one, of course, it's a little bit further off. The reason that we recommend that you start to build the capability now is because we believe a disproportionate share of the value, 90% of the value, will go to the earliest 10% of adopters. This is typical with deep techs. And we wanted to note that I think quantum computing has all of the characteristics of a winner-takes-all or winner-takes-most kind of dynamic in various industries. And so we think it's important for companies to, unite around the opportunity, to re-architect workflows, to identify talent gaps. It's the number one scarce resource in this field is actually talent. And then also to really invest in partnerships, really in some ways as a way to help make sure that you're staying current in terms of potential use cases, but also to fill that talent gap as well. When we talk to companies, the next step that they ask us is, well, how do you do this? We think that there are effectively three steps that you need to go through in order to make quantum computing a priority at your organization. The first is that you need to kind of sell it. You need to secure executive level support, funding, and buy-in. You don't want to hype the technology, but you need to show the potential disruptive impact of the technology and articulate it in clear terms that land with business leaders who will make funding decisions. The second thing is that you need to skill it. Building a capability, when we do our kind of impact of quantum assessments for companies, it tends to culminate in real enthusiasm about the technology and a desire to move forward with building a capability. But it's not so easy. One of the real barriers is that it's very, very difficult to find talent. And so one of the ways that you can do this is through partnership with some of the providers that I think you'll meet in the next 2 days. That also applies to the third portion, which is scaling it. Scaling experimentation is really the only way, fast failure and scaling, to develop the kind of IP that'll set you apart and set you up for financial success when the technology matures. We think that these are really ideal foci for partnerships with quantum tech providers. But how do you decide kind of who to partner with? If partnership is kind of the name of the game, how do you decide? We think that there are a few really important things, and we've written some recent pieces on benchmarking, right? It's one of the typical ways that you would do this in classical computing, where there are systems benchmarks. These are things like qubit counts and gate fidelities, even things like quantum volume. And then there are application benchmarks. Increasingly, application benchmarks are important, right? If you're doing chemistry, you want to take a look at relative performance on Hamiltonian simulation, that sort of thing. But we do still think that any end user that's new to the technology should really prioritize three things. Benchmarks are important, but three things. One is the talent of the company that you're partnering with. That is the scarce resource. And that's true not only for end users, but also for providers of the technology, software providers, hardware providers. So talent's critical. The second is the technical roadmap. And the roadmap needs to be ambitious, but also credible. So evaluating a company's technical roadmap is not easy, but really important. And the third one is partnership capabilities. To what extent does the company that you're considering have a history of partnering, have business skills as a complement to technical skills, and to what extent is it a good kind of culture fit for you? These are the things that when we talk to companies in this space, we try to encourage them to consider. So I think the last thing that I'll say, the thing I'll say by way of conclusion, is that as the head of deep tech in North America, I can say that there's no single technology that I'm more excited about than quantum computing. It's the thing that I get the most inbound questions about without any question. The second thing I would say is that I don't believe that quantum computing, a quantum computer, can be built without an ecosystem. And I think credit to QCware, to IBM and others for bringing, and QEDC for bringing communities like this together, because I think it really is deeply important that there's collaboration up and down the stack across countries. I think that's absolutely critical. And then the third thing that I would want to say is that it really is not too early to start taking this technology seriously. It's actually on the brink of being too late. So I hope that if nothing else, that we motivate you to really start to think about scoping a capability for your company, partnering, and really becoming a part of this incredibly important enterprise. Thank you very much.